pretty much a quadratics problem, which is fairly easy in my opinion, but context-wise it can get a little bit confusing, like what they're actually asking for. So, for number 10, we have that a player throws a basketball and the height of the basketball is modeled by this right here, where h is the height of the basketball above the ground in meters. Units are important for our answers, and t is in time in seconds. So h for height and t for time. For part A, we need to find how long it takes for the basketball to reach its maximum height. So the big buzzword here is the word maximum. So essentially, I did mention this is a quadratics problem, but let's also talk about how I know that it's a quadratics problem. And this first step is very important to acknowledge. So a quadratic, its general sort of function is ax squared plus bx plus c. Whenever you have something like this, you have what we call a quadratic. Now guys, a quadratic, you might have also heard it as a parabola. And the cool thing about the quadratic or the parabola is that it can look like this, or it can look like this. Okay? So it's either like a U facing up or a U facing down. The other way that some people memorize it is that it's either like a smiley face or it's either like a sad face. Okay? So there you have a quadratic. And in this case, there's a lot of different stuff you can learn about a quadratic, and that we're kind of gonna do it on the fly. See? So depending on the values of a, b, and c, you can identify a bunch of different stuff about this quadratic. The first thing I will explain is that the value of a, if it's positive, you have a smiley face like this guy here. If a is negative, then you have a sad face like this one here. And so for part A, it makes sense that they're asking for maximum height, because my value for A is negative. My value for A is negative 4.75, which is something that is less than 0. And so because it's negative, then you have a sad face. And if you have a sad face, notice you have a maximum. If you have a happy face, you have a minimum. So that's the first observation I'm going to make. It makes sense that we're looking for a maximum because our parabola looks something like this. Okay? The second thing I will mention is that a parabola, the other cool sort of function that it has, okay, is that no matter how it looks or how it's drawn, it has this thing called the axis of symmetry. And so when something is symmetrical, that means it is equal like on both ends. Okay? So for example, the axis of symmetry runs right down the middle. And it's no different than like you have, imagine your own face, see? And imagine you draw a dotted line that runs through your forehead, through your nose, through your mouth, all the way down. You have an axis of symmetry. Like the distance of your eye to the left is the same as the distance from that axis of symmetry to the eye on your right. And quadratics are no different. Like the distance from here to here, I know it's not drawn to scale, but the distance from here to here is equal. Like say maybe they're both 2. From here to here, maybe they're both 3. From here to here, maybe they're both 4. And the awesome thing about this, or why I'm mentioning it in the first place, is that the axis of symmetry, I don't know why I put symmetrical. Parabolas are symmetrical. Right now I'm talking about the axis of symmetry. Okay? So in an axis of symmetry, the cool thing about it is that it has to run through the max or min. The other thing you might have heard of in class is that it's the vertex. So the axis of symmetry goes to the vertex, and the vertex is either a maximum or a minimum, right? So you can have a parabola that goes like this, or a parabola that goes like that, and the axis of symmetry on both is going to be right there. And it's going to give you information of where the vertex is. So here you have, for example, vertex 1, and here you have vertex 2. And the cool thing about vertex 1 is that it's a minimum, and the cool thing about vertex 2 is that it's a maximum. So, in conclusion, a vertex can be either a maximum or a minimum. you know whether it's a maximum or minimum either visually or by seeing the value of A. So if A is negative, you have a maximum. If A is positive, you have a minimum. And yes or yes, the axis of symmetry cuts through that maximum or minimum. So the axis of symmetry is going to help us for finding the maximum height. So in conclusion, or conclusion number 2 maybe, when you read maximum height or minimum height, you have to be thinking axis of symmetry will give me the x value of vertex, and the x value of the vertex will help you get the y value of vertex. Okay, that is like the procedure we will go for. Once you find the x value of the vertex, you use that to plug it in back into your function and get the y value of the vertex. So let me make a little bit of space. It was a little bit of a long introduction, but also a very necessary introduction. So our game plan is finding the x value of the axis of symmetry is the same as the x value of the vertex. And through that, I get the y value of the vertex, which helps me find the maximum height. Now, for axis of symmetry, okay, so AOS will be for axis of symmetry. For the axis of symmetry, there's actually an equation. So the equation for axis of symmetry, which is, I don't think it's in your formal booklet. I'm pretty sure it's not. So for quadratic, we have 2 equations. Look at that. So in your formal booklet, you will find out that for the axis of symmetry, the equation is negative b over 2a. So the axis of symmetry, which is just an x value, will be negative b over 2a. And in this context, what is a, what is b, what is c? Well, let's take a closer look. A clearly has to be negative 4.75. B clearly has to be 8.75. And C clearly has to be 1.5. Guys, a classic example is that people say A is negative 4.75 t squared, or that B is 8.75 t. And there's a small mistake here. It's a common one, but it's a small mistake because your A, B, and C is simply what is defined by what is next to it. So your A is whatever is next to x squared. Your B is whatever is next to x. And I can mention the same thing here. So whatever is next to t squared is your A. Whatever is next to t to the power of 1 is your B. So here are my values for A, B, and C. And so if I go ahead and plug into negative b over 2a, I end up with x equals negative 8.75 divided by 2 times negative 4.75. And so, well, really I can just plug this into my calculator and see what happens. Because I'm plugging into a fraction, just to make it more organized, I suggest you press alpha, y equals, and then the first one. Okay, this helps you for putting in fractions. And so the first one, voila, looks like this. Plug in carefully, don't mess it up. These are easy points. Always use parentheses for plugging in multiplications. That's my suggestion. Bada bim, bada boom, there is my value of x. So my axis of symmetry is an x value, right? Which is also the x value, as I mentioned earlier, of the vertex. So that is also another thing I should maybe clarify. Whenever you use this equation for the axis of symmetry, you can also think about it as the x value of the vertex. Okay, it's the same thing. The axis of symmetry is the x value of the vertex. Once you establish that, this becomes so much more easy. So the axis of symmetry is the x value of the vertex, which gave me 0.921, 0526. If I were to do 3 significant figures, I would count 1, 2, 3. This one, do I round it up or keep it the same? I keep it the same. So significant figures, you can put the whole number, but for now I'll put significant figures is 0.921. And so the procedure that I showed you was find the axis of symmetry. This is the x value of the vertex. Use this for the y value of the vertex. And this next step is actually very simple. It's just very common for us to get confused what we're doing, why we're doing it. So right now, you have some x value. See? And if I were to plug in, so the equation of the parabola is negative 4.75t squared plus 8.75t plus 1.5. So if right now I were to plug in the x value of the vertex, so 0.921, that means I end up with an equation that looks like this. For each t value, I'll be putting that 0.921. All right? Now, this probably makes sense to a lot of you. You've probably seen it in class, but I will be in charge of explaining why. So, the big thing you're asking your function when you do this is, when x equals 0.921, what is my y? Okay, don't get lost in the sauce. This is the procedure. When x equals 0.921, what is my y? And in this context it's basically like when, or better said, if my x value of the vertex is 0.921, what is its y value? Okay, these two sentences are pretty much equivalent to each other, see? But I do need you to understand the procedure that is going on behind it. Enough blah blah, let's go ahead and plug in. So, if I plug in, I end up with negative 4.75 times the parentheses that I told you earlier, plus this. I'm just plugging in what's here, guys. Okay, don't get lost. Plus 1.5. Aha. So the y value now, or better said, when for my function of h, right, when I plug in 0.921, I end up with 5.5296. 0.5, right? And if I were to do significant figures here, I count 1, 2, 3. Do I round it up or keep it the same? Clearly, I round it up, so I'm going to leave it as 5.53. So this right here is now going to be y value of my vertex. So, look at that. I just identified let me use a brighter color for this. So I just identified the x value of the vertex, which is 0.921, and I also just found out the y value of the vertex, which is 5.53. So my vertex basically has to be at 0.921, comma 5.53. And I know that because my a value is negative, right? Because a is negative, that means I'm dealing with a maximum, right? If you have trouble remembering that, remember that if it's negative, it's going to be a sad face, okay? So it's clearly a sad face has that maximum right there, see? So instead of vertex, I'm actually going to rename it as maximum, okay? Now, context. What is my x? What is my y? Because I have it as h of t, let's remember that the original version is f of x. So whatever is inside the parentheses is x, whatever is outside is y. So clearly x is going to be time, y is going to be height. So for the maximum height, it's just the y value of my vertex. So for the maximum height for part A, I would be saying 5.53. Do not forget your units, meters. All right, so that is for part A. Pretty straightforward. Quadratics are exciting. Yeah. Then for part B, we have that assuming that no player catches the basketball, find how long it would take for the basketball to hit the ground. All right, this one also gets interesting. And I think it might make more sense if I actually explain it through Desmos. So let me go ahead and plug this into Desmos just so that we can all see it a little more, friendly. So if I go ahead and plug in my function into Desmos, and I know you might be thinking, dude, the day of the test, I can't use Desmos, but I'm trying to explain an idea here. See? So x is time, y is height. And for part B, they're asking, assuming that no player catches the basketball, find how long it will take for the basketball to hit what thing? To hit the ground. And so where is the ground in terms of height? Is the ground, you know, like up there? Is the ground here? Is the ground there? No, my dude. The ground is obviously wherever the height is 0. Wherever the height is 0 meters is going to be the height. So, assuming no one catches the basketball, the player threw it up here like this. And then where does it touch the ground? It touches the ground right there. And yes, I'm showing you the answer, but now we're going to figure out how to actually do it. See? So the one hand, I need you to really visualize and conceptualize this. For part B, if you're talking about hitting the ground and your height is your y, then all you're really finding is what we call the x-intercepts, or the zeros. Okay, it's the same thing. It's important for me to introduce the idea like this because quadratics are not that hard. I mean, for quadratics, usually what I see, okay, is that they're asking stuff like the max or the min. Okay, they're asking stuff like the zeros or the x-intercepts. Okay, they're asking stuff like the y-intercept. The tough part is that the IB loves to disguise this, you know? When they're talking about, well, when they ask about maximum height, that one's pretty obvious. But when they're talking about hitting the ground, it's disguised as x-intercept. See? And so that's the kind of stuff we need to start catching on to. That's why I'm presenting it to you in this way. So for part B, how do you find the zeros of this guy here? So let me rewrite my equation right there. H of t equals negative 4.75 t squared plus 8.75 t plus 1.5. So the three main tools that you have, okay, is technically on the one hand, okay, you can do factoring. All right, it's just that factoring here is a little bit hard. The other tool you can do, that's actually in your formula booklet, which is the other formula for quadratic, is this right here. Solutions of a quadratic equation really just makes reference to the zeros, okay? Notice how this equals 0. Why would it equal 0? Why would it make this equal 0? Because if that equals 0, then you're basically asking your function, when y equals 0, what is x? It's a little bit backwards to what we did earlier where we gave an x and found a y. Here, if you equal your quadratic to 0, you're saying when y is 0, what is x? And so you will be finding the x-intercepts when you do that, okay? All you're really plugging in is some x, you're gonna find some x when y is 0. Okay, that's what you're doing. That's all that's happening here, okay? Anyways, back to the tools. You have the factoring. You have this thing here, which is I think we just call it quadratic formula, okay? So we can use the quadratic formula, or we can use graphing, okay? I think most people use quadratic formula. It's what I show in most of my videos. Today I'm going to show how to do the graphing. See? Feeling a little bit spicy. Let's see what happens. So you know you don't have decimals. You do have your graphing calculator. So how do you solve it by graphing? Well, go to y equals and plug in your equation. So if you go ahead and plug in your equation, you might be thinking, I don't have t. Okay, but t in this context is really just an x, ¿cierto? So that means you can put it as negative 4.75 x squared plus 8.75 x plus 1.5. And from here I press graph, and it's pretty likely that it's not going to show up just because your window is not aligned. In this case, my window is aligned, but I'd be willing to bet that half of the world watching this did not have a nice window. So I'm going to give you tips and tricks on how to get a good window. See? The main tip is that you can go to zoom, scroll all the way down, and do zoom fit. Okay? Zoom fit usually helps you see like the key points and stuff like that. And so in this case, the key point that it seems to be trying to show me are the x-intercepts. And so this by itself, although it might look kind of nasty, it is a very good starting point, believe it or not. So on the one hand, clearly I need to put more y values so that this is easier to see. And all these negative y values is useless information. The other thing that might be relevant is that given the context of the problem, you only care about when the player catches the basketball, which is going forward in time, not backwards in time. So with all of that, because I'm going forward in time and not backwards in time, I can make my x minimum be 0. I don't care about negative values in this case. My y value does not have to be negative because I don't care about negative heights. So I'm actually going to put y min of maybe -2 just to see it better. My y max, well, because of zoom fit, I was able to see the maximum. I also know that the maximum is at 553, right? So I'm going to put a y max of, I don't know, 7 just to see it a little bit better. See? So it's that kind of stuff that helps you regulate how your window should be. The zoom fit was an excellent starting point, but the information that you already have from the problem helps you out. See? So from there, instead of pressing enter, you actually just press graph. Okay. And yes, there are useless x values here, but for our intents and purposes, this is good enough. What is good enough? Being able to see the x-intercept, which I clearly do. So that right there is what I need to find the zeros. See? So you can actually do second and then hit trace in order to press calc. So with that, you have a bunch of different stuff that helps for the quadratic, including the max or min actually. I could have showed you how to solve it with that as well. In this case, I press 0. See? Now notice what it asks for. It is asking for left bound, and later on it's going to ask for right bound. So let me explain that for a second. This quadratic right here that you see on screen technically has 2 zeros. It has this one and this one, right? And so if I were, this is the main idea. If I were to plug in a left bound of -3, which is this green one, and the right bound of x equals, I don't know, 3 as well, what your calculator is going to do, okay, is that it's going to basically scan between the green and the purple for any zeros, for any x-intercept. Clearly, it's going to find 2 of them, right? And so you need to be able to specify which one you actually want, which is why at the end of the process, it asks you to guess. But for us, just to keep it a little bit more friendly, we're going to keep our x or our left bound maybe right here, maybe at 1, right? And then we're going to, at 3 is fine. See, so now we're going to scan only this x-intercept. It's the only one we actually care about. So the left bound, we're going to put it anywhere to the left of my 0. So that's, this is probably fine. And my right bound is going to be somewhere to the right of my 0. That's probably fine. And then guess, see? Guess is not that your calculator is dumb and needs to know. Guess is that you're specifying which 0 you want. Okay, so that's what I meant. I suggest just keeping the bounds to the 0 you actually want. But the guess function, that's its role. You're specifying which one you actually want. See? So I press it over here. That is my 0. 2, 0. So over here, got a little bit messy, but for part B, basically, I found that my 0 was 2, 0. See? And so if my 0, my x-intercept, is 2, 0 for part B, I can say, how long would it take for the basketball to hit the ground? It would take 2 seconds. Because if my x-intercept is 2, 0, the 0 is the height. As I mentioned earlier, y is height. And the x is going to be the time. So 2, follow the units. Units is seconds, so 2 seconds. See, that is for part B. Later on, they tell us that another player catches the basketball when it is at a height of 1.2 meters. And so for part C, we need to find the value of t when this player catches the basketball. Now, another pretty easy problem. We just need to really understand what is happening here. So the first question I will ask you is, they're giving me a height of 1.2 meters, correct? What are they asking for? They are asking for when this player catches the ball. So, 2 very important things to point out. They're asking when they catch the ball, and they're telling me that we have a height of 1.2. As I just mentioned a second ago, x is time, y is height. So basically, they're giving me a y of 1.2, and they're asking what is my x when y is 2. So when y equals 1.2, what is x? That's all they're asking for. It's not that hard. The thing is, it's kind of disguised because it's like, in terms of context, it's saying when the height is 1.2 meters, what is, when is the ball caught? And so this is a very tricky way that the IB tries to ask you, quite basically, when y equals 1.2, what is x? See? So if y equals 1.2, that means this whole thing is 1.2, and x is what you're trying to find. See? So this that I'm putting now in pink is what I need to solve. See? So not that complicated. I can start off by doing minus 1.2, minus 1.2, 0 equals negative 4.75 t squared plus 8.75 t plus 0.3. Now notice this procedure that's happening right here is actually the same procedure that I did for part B, because notice I equaled it to 0 for part B. And up here I'm also equaling it to 0, and the only difference is that my C value, instead of being 1.5, is 0.3. But all I really need to do now is go back to y equals I can probably just change this to 0.3. That'll work. And then graph it. See? So when does this happen? We'll find a 0, of course. So find the new 0, and in this context, it will be $1.875. 3 significant figures would be 1.88. So for part C, just following pretty much the same procedure, we ended up with, it will happen at 1.88 seconds. Okay? So that is one way to solve it. You sort of approach it by asking yourself this. See? And now that I think about it, there's one more way to approach it, which actually might be a little more exciting or maybe more intuitive. See? So I'm going to go ahead and put back the original sort of like equation, and for my, I'm going to add another line. So this other line that I'm adding, because it's going to be a y value, it's going to be for the height of 1.2. So basically I'm having this equation here, and if I go ahead and put a y equals of 1.2, I just need to find this point right there. And so if I find this point right there, this intersection, okay, this will be when the player catches it. So notice the 1.2 is going to be the height, and that 1.875, which is rounds up to 1.88, is the moment it is caught. So that's two ways to solve it. The second way for me is actually a little more intuitive. So here I put 1.2 for the height of the player. Both lines are going to show up now. Same as decimals, both lines show up. And now I just need to find the intersect. So I can do second, trace, hit calc, go to intersect, pick your first curve. Usually it nails it right away, but just to check, there's my first curve, and the second curve is this red one, right? Guess is just for picking the intersect. This is my only one. Boom, there's the answer. I got the same 1.875. We rounded up to 1.88. Okay? So, two ways to solve for part C. Whichever one is more intuitive for you, go for it. I think most people would appreciate this one more. But this other aspect has a very visually appealing approach. Whatever floats your boat. See? There's a lot of people out there. Everyone does whatever is best for them, right? And last but not least, we have the exciting question, part D. Write down two limitations of using h of t to model the height of the basketball. And so two limitations, notice 2 points. Now, although this might be case specific for the context, there is something I can mention here. First of all, this is a classic IB question. They love to ask questions about what are limitations of your model, right? What are things that your model would maybe not be good for or good at or etc. See? So on the one hand, what comes to mind is like maybe this model, I mean, notice it has a bunch of negative values down here. See? So you can say that maybe this model is good, but not always. Like what if you have someone that's really strong, the ball would probably go a lot farther, right? And so there's all these different kind of limitations that can sort of come to mind. And I'd rather take this discussion to the answer key. Okay, it'll probably make a lot more sense if we approach it from the answer key. So in the answer key, notice, usually you just have to criticize your model as much as you can, right? So on the one hand, the model is not a physics model, it's a math model. See, if it were a physics model, it would have to take into consideration a bunch of stuff. So really, the cool thing about these exercises is that there's a lot you can sort of like, it's not that you invent it, but like you can go with your gut on this kind of stuff. See? So like you think about it, a basketball, you're trying to measure it. There could be wind, there could be rain, there could be this, there could be that. There's like a lot you can sort of say, so just go with it. The other good thing about this kind of context question is that it doesn't use anything from part A, B, or C. Nothing at all. Nada. You can go straight to part D. Why would you ever want to go straight to part D? If you're running low on time, if you want to get some free points, identify the questions that are context questions. Okay? Once you realize that part D is a context question, maybe if you're running low on time and you want some free points, just do part D. Don't do anything else, right? Or maybe you did part A, got stuck on part B, noticed that part D was a context question. You have 5 minutes left in your test. You're going to do part D, right? After all, these are all worth 2 points. Keep that in mind. Enough blah blah, back to the discussion. There's a lot of stuff you can say here. You can say it ignores wind resistance. It treats the ball as a point. It assumes that gravity is constant. Maybe there's like a little bit of height on the ground. Maybe there's not. I don't know. There's a lot of stuff. See? It assumes the ball continues to follow the trajectory even after hitting the ground. That's another good point. That's what I meant about there's a bunch of negative values here, right? Doesn't account for that. Like an actual model would probably have more bounces from the basketball, right? And the model ignores the bouncing ball, just as I said, back of the ball after hitting the ground. See? So as long as you don't keep it as something generic, you're gonna be okay, right? Don't say that there are assumptions being made. Mention one. Mention one. Okay? Don't say that models are never accurate. Say why. Right? So mention something. The main idea I need you to get from this is that you need to be specific. As long as you're specific and you just kind of like say some stuff, you're gonna get the marks. See? Ladies and gentlemen, that was a quadratic problem. I like quadratic problems. They're exciting. There's usually only a couple of stuff they can say. Max or min, zeros, x or intercept, and y intercept. The thing is they disguise it through the context. So watch out for that. But keep in mind, there's not too much they can ask from you, and there's not too many tools here either. Okay? So as long as you have them clear, this is a sort of exercise that, yes, there's a couple procedures, yes, it's some writing, but it's solid points. So quadratic functions should be solid points for you. And there it is. I hope it helped. I'll see you around, and take it easy.